Hey guys, so this is lesson 7. We're going to kind of switch gears here a little bit. For most of the class, we've been talking about trigonometry, trig equations, trig identities, trig functions. Now we're going to switch gears a little bit. So the coordinate system you're used to is called the Cartesian coordinate system, and that involves an x and a y axis like this. So we have an x-axis, a y-axis, and a point is described somewhere in that space by an x-coordinate and a y-coordinate. So this is called the Cartesian coordinate system. But sometimes we have equations that are not so easily described in this system. So we want to use a new kind of coordinate system called the polar coordinate system. So in the polar coordinate system, we have a point at 0 that we call the pole, and in the XY system, this is referred to as the origin. And from 0, we have a ray, which is a line that goes in one direction, and that's called the polar axis. So I'm going to draw you a little picture to make this make a little more sense. So the polar coordinate system, we have a point at 0, and our polar axis extends out from 0 to the right. So it's kind of like the positive x-axis. And what we do is we go some angle away from the polar axis in the counterclockwise direction. So let's say that I went some angle away from the polar axis, and we'll call that theta. And let's call this distance right here r. So this is r, and that's going to be a distance. And so any point, we'll call this point P in the polar coordinate system, we're going to describe with a coordinate r, comma, theta. So instead of x and y, you have a radius and an angle. So if you were actually looking at some polar coordinate graph paper, it kind of looks like the top of a globe. So you would have like the pole there, and then you might have a little circle at radius 1, a little circle at radius 2, and so on. But this polar axis is going in that positive x direction. So what we want to do is go out our radius distance and then around counterclockwise for some angle theta, and that would describe the point. Okay, so that's the polar coordinate system. So we're going to practice graphing a few of these now. So, alright, so each point in the coordinate plane is going to have a polar coordinate, which is still an ordered pair of the radius and then the angle that we're going around. So, as I said before, r is going to be a directed distance, and theta is going to be a directed angle. And all we mean by directed is that r and theta can be positive or negative. Okay, so we're going to practice plotting a few points in the polar coordinate system. First, we have the point 2 comma pi over 3. So r is equal to 2 and theta is equal to pi over 3. So all this means is that we start at the origin, we go out to the circle of radius 2, and we go around that circle until we hit the angle pi over 3, or as our graph paper says, 60 degrees. So the point 2 comma pi over 3 would be right there. Alright, let's try another example. Next we have the point 3 comma negative pi over 6. So our radius is 3, and theta is negative pi over 6. So again, we'll start at the origin, go out to the circle of radius 3 this time, and since our angle is a negative pi over 6, we're going to go in the clockwise direction for 30 degrees, and so the point would be right there. So that is where that point would be. Alright, we'll do one more example. For the point 3 comma negative 11 pi over 6, again our radius is 3, but this time our angle is negative 11 pi over 6. So we'll start at the origin, go out to the circle of radius 3, and we'll go around that circle until we hit negative 11 pi over 6, and that would be right there. So this point is going to be right there. And so if you notice, this is kind of the same thing as if we had gone out to 3 and then around positive pi over 6. So this is kind of an important thing to keep in mind. Just like on the unit circle, when angles could be named different things, we have the same thing going on in this polar coordinate system. Unlike the xy plane where the point, say like 2, 2, means the point 2, 2, in the polar coordinate system, one point can be named in many different ways. So that's what we're going to look at now. So if we're given a point, r comma theta, one easy way to get a different point in the same position as your original point is if you were to just add 2 pi or some multiple of 2 pi to your angle. So you can think about that as you've gone around the circle some k number of times. So that's one way to get it. Another way to get an equivalent point is if you make the radius negative and then add an odd multiple of pi to your angle. So that's another way to get an equivalent point. But as I said, the easiest is just to add some multiple of 2 pi to your angle. So we're going to practice a little bit by finding 3 additional polar representations of the point 3 comma negative 3 pi over 4. So let's think about where negative 3 pi over 4 is on the unit circle. So if those are my axes, negative 3 pi over 4 is going to be over here. So we have, that's negative pi over 4, negative 2 pi over 4, negative 3 pi over 4. So that's kind of where my angle is, and we've gone out a radius of 3. So what's another way to name this point? Well, if you think about this as being 0, what if we had gone around in the positive direction, so around this way, instead of in the negative direction? Well, it's not too hard to figure out what that angle is. So we know that one full rotation around the origin is going to be 2 pi. So if this is negative 3 pi over 4, then if we were to start here and go this way, it would be 5 pi over 4 to end up in the same spot, because 5 pi over 4 plus the 3 pi over 4 would give us the full rotation, because that would give us 8 pi over 4, which is 2 pi. So with that in mind, that tells us that 5 pi over 4 is another way to represent the angle negative 3 pi over 4. So an equivalent point would be 3 comma 5 pi over 4. So that's one way to do it. Another thing we could do is just keep adding 2 pi to the angle. And so if we did that, we could definitely get some equivalent answers. So, but let's try and turn the radius negative just so you can see how that works. So if I want to make the radius negative to find another equivalent point, so let's think about if we went this way 3 units instead of to the right. So if we have our point out here and we want to rotate around until we get to negative 3 pi over 4, how far would we actually go? Well, from this axis, we're only traveling pi over 4 to get to the point we want. So our new angle is going to be positive pi over 4. All right, and to get another equivalent point with an r coordinate of negative 3, you could just add 2 pi to this pi over 4 or subtract 2 pi. So in this case, I think I'm going to subtract 2 pi just so we can see what that ends up as. So if we were to do 8 pi over, or sorry, if we were to do pi over 4 minus 2 pi. That would be pi over 4 minus 8 pi over 4, which would give us negative 7 pi over 4. So that tells us that this point right here is in the same position as this point, and of course the original point that we had. So those are some ways that you can find different names for the same point. Okay, so what we're going to look at next is, well, what if we had something that was in polar coordinates, or we had something that was in XY coordinates, which we sometimes call rectangular, because your grid is, of course, in a box or rectangular shape. So we're going to look at how to go between these two coordinate systems. So these equations below are some good ways to do that. The first two are useful for if you want to go from polar to the XY coordinate system. And the second two are useful if you're starting in XY and you want to go to polar. So those equations are useful for converting your coordinate systems. So let's practice with a couple of examples. So we want to convert the polar coordinate 2 comma pi to rectangular coordinates. So I know that to convert to rectangular coordinates, I'm going to need an x coordinate and I'm going to need a y coordinate. So to find the x coordinate, from the equations above, we know that x is equal to r times the cosine of theta, and we know that the y is going to be equal to r times the sine of theta. So from our polar coordinate, we know r and theta, so we can plug those values in. So we get 2 times the cosine of pi, which is 2 times negative 1, which is negative 2. And for the y coordinate, we have 2 times the sine of pi, which is 2 times 0, which is just 0. So what this has done is this has told us our x and our y coordinates. So the last thing we need to do is just rewrite the x and y coordinates in the form of an ordered pair. And so that's negative 2 comma 0. So that is the converted polar coordinate to pi, becomes negative 2 comma 0. So let's try another example. This time we have the square root of 3 comma pi over 6. So we're going to do the same kind of thing. We know for a rectangular coordinate we need an x coordinate as well as a y coordinate. X is equal to r cosine of theta, and y is equal to r times the sine of theta. And once again, we know the values of r and theta because of the way that our point is written. So we can go ahead and plug these in. So for the x coordinate, we get the square root of 3 times the cosine of pi over 6. And for the sine, we get the square root of 3 times the sine of pi over 6. Alright, so for the x coordinate then, we get the square root of 3 times the cosine of pi over 6, which is the square root of 3 over 2. And so if we were to multiply this across, we just get that the x coordinate is equal to 3/2, because this square root is going to cancel with this square root, and we're going to be left with just the 3 underneath. Now for the y coordinate, we have the root 3 times the sine of pi over 6, which is 1/2. So if we multiply this out, we just get it's the square root of 3 over 2. So again, the last thing I need to do, now that I've converted each coordinate, is simply to write it as an ordered pair. So I write my x coordinate 3 over 2, and my y coordinate root 3 over 2. So this is the converted coordinate. Alright? So that's going from polar coordinates to xy coordinates. The one we're going to do next is we're going to look at a rectangular coordinate and try to turn it into a polar coordinate. So again, the second two equations in that list will be very useful here. So what we're going to look at first is converting the rectangular coordinate negative 1, 1. So we know for a polar coordinate, we're going to need an r and we're going to need a theta. So if we use the equation tangent of theta, is equal to x over y, y over x, we can solve for theta because we know that we know x and y in a rectangular coordinate. So let's go ahead and plug those values in. So we have that the tangent of theta is equal to 1 divided by -1, which is just -1. So now what we need to do is think about where on the unit circle do we get a angle that has a tangent of -1. And one important thing to consider here whenever you're doing this is what quadrant are we talking about? So if you look at the coordinate -1, 1, and you think about your rectangular coordinates, you know that you'd have to go over 1 to the left and up 1. So that puts us somewhere in quadrant 2. So the important thing to consider when you're thinking about angles is, well, is my angle in quadrant 2? So what we're looking for is an angle in quadrant 2 with a tangent of -1. And the angle that fits that bill is 3 pi over 4. So that would be the easiest angle to look for. Of course, you could do a negative angle, or you could add any multiple of 2 pi to 3 pi over 4, but I think that that's the easiest one to think about, so we'll go with that one. So theta will be 3 pi over 4, and now what we need to do is figure out our radius. So if you look at the fourth equation on the list, we have r squared is equal to x squared plus y squared. So this is going to be how we get r. So again, we know x and y, so we can plug those values in. So we have -1 squared plus 1 squared, and that will give us 1 plus 1, which is 2. So what we have is r squared is equal to 2, and so if we square root both sides, we get that r is the square root of 2. So the very last thing to do is just to write our answer as an ordered pair, which in this case will be the square root of 2, comma 3 pi over 4. So that is the point -1, 1 converted to polar coordinates. All right, we'll try one more example of this. This is the point 0, comma 2. So again, we know our x and y, and we want to find r and theta. So to find theta, we'll once again use the tangent equation, and we'll sub in our values of x and y. Now what you should notice here is that I am starting to divide by 0. Now that is bad. We don't want to divide by 0. So what we need to do is think about at what angle on the unit circle. So let's think about our xy coordinate plane. The point 0, 2 is going to be on this positive y-axis. So the point on the unit circle that falls on this positive y-axis occurs at the angle pi over 2. So we can say that theta is going to be pi over 2. We can't actually solve it with a tangent inverse or anything because the tangent is undefined because of this 0 in the denominator. So we need to just say that our angle is pi over 2. Next, we need to get the radius, and so again we use that r squared is equal to x squared plus y squared equation, and we can plug in our x and y. So we get that r squared is 0 squared plus 2 squared, and that gives us r squared is equal to 4. And if we square root both sides, we get that r is just equal to positive 2. So now that I have found r and I've found theta, the final thing to do is just to write this as a point. And so that would be 2 comma pi over 2. And so that is the point 0 comma 2 converted to polar coordinates. Okay. So moving on to the next page. So now that we've converted coordinates, one thing you might be wondering is, well, can we also convert equations? Because remember I said at the beginning that some equations work out much more nicely in polar coordinates than they do in rectangular. So this is really like our big goal with polar coordinates, is how can we get these rectangular equations that are really messy to look really nice by converting the equation to polar coordinates. So it's the same equations we used before. x is going to be r cosine theta, y is going to be r sine theta. So this is whenever we're starting in a rectangular equation and we're going to a polar equation. So let's do an example with the rectangular equation y equals x squared. So as I just said, I would start with your equation, so y equals x squared, and we want to plug in r sine theta wherever we see a y, and r cosine theta wherever we see an x. So we end up with the following. Now if I actually square this, I get that r sine theta is equal to r squared times cosine squared theta. And my goal now is to solve for r. So just like in the rectangular system, when we like things to be solved for y, in the polar coordinate system, we like things to be solved for r. So we're trying to get r by itself. Okay? And the way that I would do this is, I notice that I have an r on both sides. So I'm going to divide by r on both sides, and I'm going to divide by a cosine squared. So that will move the cosine squared over with the sine, and it will move the r away from the sine over with the r squared. So that's what we're going to do. So now on the left side, the r's cancel out, and on the right side, the cosine squareds cancel out. And we get that r, so if we do r squared divided by r, that gives us r. So r is equal to sine theta over cosine squared theta. And we can simplify this a little further. So if we think about this as sine theta over cosine theta times 1 over cosine theta, we can say that sine over cosine theta is tangent of theta, and 1 over cosine of theta is secant of theta. So r equal to tangent of theta secant of theta is our polar equation. All right. Now, so that was starting in rectangular and going to polar coordinates, but what if we wanted to go from polar to rectangular? Now, this direction is not quite as straightforward. We can't just substitute some value for r or for theta. What I think is very useful is to think about it geometrically. So think geometrically in these cases. So if we think about the equation here, r equals to 2, let's think about what that would look like in a polar coordinate system. So remember, for a polar coordinate system, what we have is we still have kind of 4 quadrants, but our main axis is that positive x-axis. And what happens is we have a radius of 2, but we have this at every single angle. So we're saying that there's this constant radius of 2 from that origin, no matter what the angle is. So if you kind of think about what all those points would do at a constant radius of 2, you might notice that they make a circle. So this is actually just a way of writing a circle of radius 2. So as I said, some equations look a lot nicer. To me, r equals 2 looks a lot nicer than the x squared plus y squared equation that you would see in the rectangular coordinates. And so that's why polar coordinates can be very handy. Now, if we want to translate this back, though, we need to think about what the general equation of a circle is. So if you remember, a circle centered at the origin is going to be x squared plus y squared is equal to r squared. But we know that r is equal to 2, so we can go ahead and plug in 2. So we have x squared plus y squared is equal to 2 squared, and if we just simplify that exponent there, we get x squared plus y squared is equal to 4. So that would be the rectangular equation of r is equal to 2. Okay? So we'll do two more examples with this. The next one is theta is equal to pi over 3. So again, let's kind of think about what this would look like in the polar coordinate system. So if theta is equal to pi over 3, we're not specifying a radius here. So the radius could be anything, but the angle has to be at a constant pi over 3. So if you kind of think about this, we'd have, these points all following this line that is angled to where it goes through pi over 3. Okay, so this is going to be a straight line. And so we know that any straight line in the xy plane can be represented with the equation y equals mx plus b, where m is the slope and b is the y-intercept. All right, now in this case, we know that the line goes through the origin, so b is going to be equal to 0. Our main problem is, how do we find the slope? Well, let's think about the equations that we have available to us. So one equation we haven't used yet is the tangent of theta equal to y over x. And if you think about what slope is, well, slope, or m, you might remember this equation from algebra. We have y2 minus y1 over x2 minus x1. This is basically the y over x that we see in the tangent equation. So we know that theta is pi over 3, so we have the tangent of pi over 3 must be the slope. Okay, so that's a little hard to wrap your head around, so if that doesn't make sense, please let me know and I will try to explain it to you a little bit more. But basically, when we look at a tangent, it is the slope. So the tangent of pi over 3 we know is equal to the sine of pi over 3 divided by the cosine of pi over 3. So the sine of pi over 3 is the square root of 3 over 2, and the cosine of pi over 3 is 1/2. So if we divide these two fractions, we get square root of 3 over 2 times 2 over 1, which makes the 2's cancel, and so we get that our tangent is the square root of 3. So because the tangent is the square root of 3, the square root of 3 is our slope. So we can plug this into our slope-intercept form. So we get y is equal to the square root of 3 times x, and our y-intercept was 0, so we don't really need to worry about that. So this is our rectangular equation that goes with theta equal to pi over 3. So in this video, I'll do one last example where r is equal to the secant of theta. So again, let's kind of think about this geometrically. So we know that r is secant of theta, and we also know that secant of theta is 1 over the cosine of theta. So if we were to multiply cosine of theta to the other side, let's see what happens here. So we get r cosine of theta is equal to 1. Now, r cosine of theta, as we found out earlier when we were going the other way, r cosine of theta is equal to x. So what we can say is that the entire left side of this equation is x, and that is equal to 1. So what we get is that x is equal to 1. And this is actually an equation in the rectangular coordinate system. So if you have an equation of the form x is equal to some number, this is always going to be a vertical line. Okay, so if we were to look at this graph, basically what you would see is you would see a vertical line at the coordinate x is equal to 1. So that's kind of what this would look like. Alright, so that's the first part of lesson 7. Hopefully that wasn't too confusing. Just make sure to work on the homework down here. Not too many problems for now, but it's important that you get some practice with this because the next part will be a lot more difficult. Alright, so I'll talk to you all next time.